Okay, so we just looked at our first example of law of sines, and it was a side-side angle case. And remember, in a side-side angle case, there's the need to introduce the inverse sine function. And if that's the case, we have to remember that we're introducing it. We need to consider all possible triangles or all possible angles that have that sine ratio. In that example we just did, one of them, okay, thank you. One of them did not work. And so we're going to see in these next two examples that what happens if it does work, or what happens if something completely goes wrong. Okay, so and again, that's why it's called the ambiguous case, because you don't know until you start solving how many triangles you're going to get. We saw one, and there's actually a case we could get 2 or 0. Okay, so I'm going to set up this triangle, and I have a low pen battery, so I'm hoping it can last. It says gamma is 50 degrees. So if I call this 50 degrees, then side opposite is C, so that's 1. And this is alpha is 2. So, okay, great. Sorry, A is 2, so it means alpha is across from that. And so then I'm missing side length B, and this is beta. So if you take a look at what is it that you're given a side and a side and an angle. So again, we're sitting inside side angle. And notice that I'm trying to spell it appropriately, not backwards, but side angle, this ambiguous case. So I have to worry that I'm introducing inverse sine. There could be more than one possible triangle. There could be 2. So let's go ahead and solve this. And so I'll say sine of 50 degrees divided by 1 is equal to sine of alpha over 2. So I'm going to cross multiply. So 2 sine of 50 degrees equals sine of alpha times 1. And then again, notice I have to do the inverse sine function. The inverse sine of 2 sine of 50 degrees. That'll be my value of alpha. So again, I'm going to type this in. So 2 sine of 50, and then do inverse sine of that. Now, don't panic. You should have gotten an error, right? You should have gotten an error because when you did 2 sine of 50 degrees, you're getting 1.532 and some change, right? Okay, so you're basically trying to do the inverse sine of a value that's bigger than 1, right? And if it's bigger than 1, that means that you can't have a sine ratio, right? You can't have a sine ratio that's bigger than 1 because the hypotenuse can't be bigger than the adjacent piece, or the opposite piece. So in this case, there are no possible triangles. This is an impossible triangle. And the reason it's an impossible triangle is because if I really were to have drawn this to scale, this length of 2 compared to the length of 1, that's 1 and that, let's say 2, if this over here is a 50-degree angle, that this 1 isn't going to extend far enough to get down to the opposite side. So it's an impossible triangle. There are 0 triangles. So part of this side ambiguity, side angle ambiguity, is that sometimes you're going to get a situation that doesn't even work. And it's in algebraically or trigonometrically, you'll know that because you'll get a sine ratio that you cannot solve. Okay, so our last example of an side angle is going to show us what's going to happen if we actually get 2 triangles. Okay, so again, set up your triangle, and it doesn't really matter. I just draw a generic triangle here, and it says that 35 degrees is alpha. So opposite of that would be 6, because that's A, and then say B is 8. So opposite of that would be beta. Here's my gamma, and here's my C. And again, take a look at what you're given. You're given a side and a side and an angle. So side, angle. So I should anticipate using the inverse sine function, and I should anticipate things that could go wrong. Like, my sine ratio could be bigger than 1, that I have no triangles, or my sine ratio could fit just 1 angle, or it could be 2. And so let's take a look. And in this example, I think I've already kind of foreshadowed that we should get 2 different triangles. So let's see what happens. So sine of 35 degrees compared to 6 is equal to sine of beta over 8. Okay, so I'm going to cross multiply, and notice I'm going to have to introduce the inverse sine function. So 8 times sine of 35, 8 times sine of 35 divided by 6. So I'm getting a ratio, the sine of beta is equal to 0.7647. And remember, there are two possible places in the unit circle that could have that ratio of like 0.76 something, like it's positive. So it's either in quadrant 1 or it's in quadrant 2 as a reference angle, which means I'd have to do its supplement. So I'm going to get two different betas. So the calculator beta, if I do inverse sine of that ratio, the calculator is telling me the beta is 49.886. Yep. But then I also know that another angle exists that has that same sine ratio. If I do 180 minus that, as if that 49.886 were actually like it's a reference angle up here in quadrant number 2, 130 degrees, 0.114 could also work. And so then let's compare that, because last time we did this, it contradicted the other given information. We know that alpha in both triangles was equal to 35 degrees, so call it alpha 2. And so if I figure out, okay, do I have enough to have a gamma? I certainly do. So if I subtract each of these from 180, so 180 minus 49.886 minus 35, I'm getting one of my gammas to be 95.114 degrees. And if I subtract these over here, 180 minus 130.114 minus 35 should be 14, so 0.886, just a little tiny guy. Now, one thing that students sometimes make a mistake on is they initially think that this angle and this angle need to be supplements, and they don't. Okay, the only supplemental pair is when you actually had to introduce the inverse sine function. So that's the only time. So it's just that one set of angles here. That's the only pair that's supplemental. The other one is based on making sure that everything adds up to 180 degrees. So I know that these three angles add up to 180 degrees, and I know that these three angles add up to 180 degrees. Okay, so now I need to find my missing side length C. And notice that side length C is opposite gamma. And there were two different gammas. So when I solve my law of sines to solve for C, I'm going to have two different equations. So I'm going to say, okay, so sine of sine of 95.114 divided by C, call it C1, is equal to, and I could say like sine of 35 over 6. Cross multiply, so 6 times sine of 95.114 divided by sine of 35. So one of my C's, oops, sorry, my bad. Oh, my pen is going crazy. C1 is equal to 10.419. Okay, so that's 1. Now, to get the other one, I'm going to do my gamma to be the 14. So very similar, sine of 14.886 divided by C2 is equal to sine of 35 over 6. Again, we're trying to find the sine of an angle over its opposite side equals the sine of an angle over its opposite side, that ratio. So then I cross multiply. Again, you can't see this, but you might be hearing the click, 14.886, and then divide by sine of 35. So now I'm getting C2 to be equal to 2.687. 2.687. Okay. So when you're in the situation where you have two triangles, I think it's helpful to subscript them, like I did. So like one of them, the missing pieces I had to solve for. Let's go ahead and just go, I guess, blue. So like beta, angle beta in the first triangle was 49.886. Gamma in that triangle was 95.114. And then C in that triangle was 10.419. Then in my second triangle, my second beta was equal to 130.114 degrees. My gamma was equal to 14.886 degrees, and my C2 was equal to 2.687. Okay, now again, side angle is going to be a big focus in this particular section because of its ambiguity, because there are possibility of having no triangles, one triangle, or two. And I know we've only seen like one example of each so far. And part of the homework is practicing that and kind of working through those problems. I'm going to put another video just kind of highlighting and demonstrating why you could get 0 triangles, 1 triangle, 2 triangles with like some animation and showing like the different cases given this, like why does this happen? But if you think back to your honors geometry days, you should think about like what were the different ways we proved triangles congruent, like SSS and SAS and ASA and the HL postulate. We should remember that one of them is not side-side angle. And side-side angle doesn't work because if you are given side-side angle, two sides and a non-included angle, you aren't guaranteed that you'd have two congruent triangles. Like these two triangles I've just solved for are not congruent. They have different side lengths. But they still share two sides that are the same and one angle that's not included that's the same, but the other pieces don't match up. So I just kind of wanted to tie that back into that particular thing from geometry a while ago. Okay. So the cases we haven't seen yet is if we're given 3 sides, or if we're given 2 sides and an angle that is included, the side, and side angle side. You cannot set up a ratio for law of sines. So instead, you need something that's called law of cosines, and that'll be in the next lesson. So you'll keep working on homework, keep looking at the examples, and then email me if you have any questions, and we'll keep going from there. All right, very good.